So thank you very much for joining my talk today. Thank you very much for introducing me. So it's exactly 2,770 deaf people 2024. This is also a critical number, but the most or even more critical number is that 92% of these are related to human mistakes that caused the deadly accidents. And this is why the industry and the research is focusing on autonomous driving, because this technology promises to avoid these numbers or reduce these numbers. And we call this Vision Zero because the vision is that we bring this number from roughly 3,000 per year to zero. And on the way, there are different strategies to achieve this goal. So the key motivation for our research in Ingolstadt at the AI Motion Bavaria Institute is to bring this number of deaf people caused by car accidents towards zero. The technology of autonomous driving is there for a few years. So you may have heard about autonomous driving cars, level 3, level 4, already about 8 to 10 years ago. And believe me, we thought and we were sure that we are close. I was working for Audi back then. We presented the new A8 in Barcelona. I was there to present it, and we promised that the level 3 system will be there in 1 or 2 years. It's still not with Audi. So what are the reasons for that? So back then, the idea was that with the new AI technology, we can solve one of the biggest problems, which is the perception. And perception means that the car knows what is around it. Then after doing the perception, you can do a planning and a control and then steer the car safely towards the traffic. And it turned out that actually driving a car is much more complicated than we thought back then. So the easy cases or the problem that has been solved very quickly is that this works in 95 to 99% of the cases. So when you go to the A9, drive from Ingolstadt to Munich, this is a traffic scenario where you follow a car on your lane that is easily doable with a level 2 system already, which can be done with a level 3 system. But this is not always the case. There are rare cases and there are complicated scenarios. So we need to distinguish between both of them. So a rare case is some corner case or something that doesn't happen very often. So for example, you are driving in the city and then there is someone coming on a bike, and for some reason this person falls off the bike. So your attention is at this specific scenario, and then there's also maybe someone driving a scooter, and the attentions of this person driving the scooter is also with this bicycle accident. So the scooter merges your lane. And you do not see it because your attention is there. So this is rare cases that you cannot capture when you collect data. So to tackle this, we are working on AI models that have a general understanding of the world. So the latest research is incorporating large language models, so AI systems that can really have some intelligence, have some world understanding. So this helps in solving these rare cases. The second thing is the complicated cases, the complicated scenarios. And they do happen all the time. So if we go to a complicated crossing, for example, in Ingolstadt or in Munich, you're always, with your car, you're getting into scenarios where you cannot see. As a human, you cannot see all the crossing. Also, the sensors of the car cannot perceive all the crossing because there's a truck next to you, so you do not see what is beyond this track. And this is what we are researching in Ingolstadt on. So this is an actual picture from Google Maps, but it's not how it looks like in Ingolstadt. So the construction site is finished now. We have a huge institute here, which is funded by the High-Tech Agenda Bayern. And what we plan to do, or what we currently do and develop in Ingolstadt, is we want to have all the equipment and provide all the data that is needed to do autonomous driving research in Ingolstadt, in Bavaria. And for this, we provide some equipment. So I am a professor for computer vision. So currently run a research group with about 7 PhD students. And we do quite some projects, but the main research interest is in cooperative perception. And cooperative perception follows the following idea. So except of only relying on the sensors that we have in the car, we also utilize the sensors that are around. So if you have a car which is equipped with a camera and LiDAR sensor and you drive around in some rural area, this is okay. Yeah, this is enough. But sometimes you get into these complicated situations, and then we guess or we assume that today and in the future there will be other cars around which also have cameras and LiDARs on it, and there might be infrastructure sensors, yeah, that have a top view of the crossing, also with cameras and LiDAR. And we want to utilize, or we utilize all of these sensors cooperatively to have a perception that uses all the information that is available and then provides it to the single agents that run there. So for this, we have currently 2 cars running in Ingolstadt, and we just bought a third one. So these 2 are here for data collection. As we are in Bavaria, we bought 1 Audi and 1 BMW. As we are in Ingolstadt, the third car will be an Audi again. Yeah. So these 2 cars are equipped with some sensor set that we will have a closer look on the next slide, but they actually cannot be driven autonomously. Yeah, so they are only there for data collection. The third car that we that we bought already is currently under construction so that it can also drive autonomously. So we integrated a steer-by-wire system so that we can steer the car fully with software. Good, so what is this strange topping here on the car? So this is a system that we bought from a company called RoboSense, and the advantage of this system is that it's flexible. Yeah, we can just put it on the car, and then we can also put it back in the lab and do some tests there. So it's removable. So this has a Ruby Plus 128 beam LiDAR. So a LiDAR is a sensor which sends out light beams, laser beams, and then measures the time until it comes back. So it can measure distance. So you get a 3D point cloud. Yeah, we will see this on the next slide. And it's equipped with 6 sensing cameras to get RGB information of the scene. So in addition, we need some GNSS system. So the GPS system that you have in your standard cars can have up to 10 meters of inaccuracy. So this is why we use a special GNSS system with multiple antennas. It's quite expensive. This is why it's not in the normal cars. But there we get accuracy of up to 1 centimeter. And of course, we need to have some car PC, which can collect this data and work with it. And we also have a radar system from Arbe Robotics, which is an imaging radar. So this is also not the standard radar system that you get in consumer cars, but this has a high resolution leading to some point cloud-like structures in the data. Good. So next to the cars, in Ingolstadt we have something that is really special. So this is not present in Munich or any other city in Germany or Europe. We have a real city lab where we put at 3 different unique positions in Ingolstadt. We put these pillars with infrastructure cameras. So we have some thermal cameras to preserve data privacy and some LiDAR sensors. And they are there 24/7. Yeah, it's not that we just put them there for testing. They are there all the time and getting information about the traffic. And as I said, there are 3 distinct locations, and this is a triangle. Yeah, so we can drive around with the 2 cars in this circle and then get some data, collect some scenarios. So next to this, we also provide a HD map for research development, as well as a Carla simulation. So for those of you who don't know Carla, Carla is the state-of-the-art software in research, used in research for simulation. Yeah, so you can play some car there. You can imagine it like a video game. Yeah, the car is driving around in a video game, like in GTA, GTA 5. And we can do all the testing in here, and we really 3D modeled this whole crossing section in Carla. So every fence, every polar, every color of a window is one-to-one mapped here, so we can do virtual development for our perception and driving algorithms, and then put it on the car and test it on the crossing here. And we're gonna release a data set that we collected here, the color map and the HD map at the end of the year. So to research in the whole world, everyone can use it then. So how does this look like? What we see here is a collection of this data set that we collected for these mentioned complicated scenarios in traffic. So this is one of the crossings that we just saw on the previous slide. And what we can see here is the fused point cloud of all the LiDARs. So we have the LiDAR system from the pillars and the LiDAR system from the cars. And we fuse all the 3D information into one huge map. Yeah, this is what we get here. So this is a video, but the real 3D map could be rotated and you can see it from different angles. But for the video, we created a bird's eye view, meaning we see everything from the top. And what can be seen here is, maybe if we start the video again, you can see a green car and a yellow car. So this is our BMW and our Audi, so the test vehicles that we just saw, driving in this crossing. And we can really see this is a very crowded scene, complicated scene. There are, if you have a closer look, there are some bicycles here, there are some pedestrians in the scene, and there is something special. So did you notice it? There are some cars standing here, let's run it again, that don't move. So now if we have a look at the cameras from the cars, which are on the top row, and the cameras from the infrastructure sensor, we see actually that there is an accident that happened. And this is one of these rare cases that you do not get very often in your data collection. We got one, and we basically see that they are standing here, and then everything, the whole scene gets off the standard. Yeah, so people are trying to drive around and stuff, and this is these rare cases that I spoke about. And here with this infrastructure sensor, we can really have like the whole scene understanding, derive the correct driving strategy, and then play it back to the cars. And what we did with this Kiwi crossing, yeah, in Ingolstadt, which on this bigger map of Ingolstadt is this is this triangle that I introduced a few minutes ago. So now we extend this to about 30 kilometers of track in Ingolstadt. So this is a real city lab, yeah, where we can drive around with the cars, collect data. We still have these 3 pillars here for data collection, but we also have another 3 mobile masts that we can place at arbitrary positions along this track. Yeah, so we can go to some crossing in here and place it there to also collect data there. What we already did is we have, again, a color 3D map of this whole track, yeah, which was manually created. So really, again, every pillar, every color of every building, every form of every building was built one-to-one in color so that we can drive around at this track, yeah, and collect some data, and then we can re-simulate this data in our color simulator, try different strategies, and test it in here. Also the HD map, we also collected a data set there, and also this 3D map and the data set that we collected is going to be released for research purposes, maybe at the end of the year or next year. So this is always, I cannot tell you a date, yeah, because you know the scientific process. We need to write a paper, we submit it, it gets reviewed, we need to rely on it, that it gets accepted and so on. Okay. So next to this data set and this cooperative perception, we of course need some equipment to run all these algorithms to train our AI models. And we are in a lucky situation, yeah, because we got some funding from the ministry. We have our own high performance cluster with about 30 H100 cards where we can train these models, and some other cards. We have access to the Bayern KI cluster, where there's also a big number of GPUs available. We have some OVX server, which is specific hardware from NVIDIA to render simulation environments. And we are currently building the Digitalbau. So the whole ground floor here will be used for AI laboratories. And yes, this is actually the last slide that I have. So I see that we have 15 seconds left, and you're already standing here. So if you have some questions, Do we have time for questions, or should we do this afterwards?
First, we can have one question.
Yes, sure. Yes.
Good. Make it quick.
Thank you so much. Have you ever faced a lawsuit due to an accident, a liability, maybe a civil or criminal in nature? And very quickly, as we know, Tesla doesn't use other sensors. They rely heavily on their cameras.
Yes.
Isn't it too risky?
So this is a big question. So I was invited to the Tesla safety days like 1 year ago, and there they spent this whole conference explaining why they only use cameras. So what Tesla has is a camera system, and in the early models they had some radar. And what they observed that in any critical situation, the camera system was enough. So the camera did detect the critical situation before the radar. This is why they stopped it. What they do not use is LiDAR. And LiDAR is if you ask me, it's a critical sensor because it really measures distances. Everything that you get from a camera, every distance information that you get from a camera is only estimated. Yeah, and this can be error-prone. So it is risky, but of course the LiDAR is expensive, and this is the reason why they don't have it in the car. But Tesla is not like, so this is sometimes a bit misunderstood. Tesla is not hating other sensors. Yeah, they say, currently it's not worth putting the money for the sensor into the car, but if this changes and we observe that it might have a sense, then they will include it in the car and sell their cars with LiDAR sensors. But currently, as far as they say, it's not necessary. If you have a look at the videos of their accidents, it might be.
Well, thank you so much, Thorsten.
Thank you.
Schön.
Yeah.
Please give a big hand.